Today, we will see in detail the Koch transformation and Coulomb Koch. In my previous class, uh, that in previous class on scalar and vector potential, we have seen that the electric field can be written as minus partial time derivative of A minus gradient of pi, where A is the vector potential and pi is the scalar potential. You know very well that gradient of scalar is analogous to a vector, and we have seen in the same lecture that the magnetic field is equal to curl of A. So now if we transform the vector A to A prime, we choose that A prime is equal to A plus gradient of chi. See, this gradient of chi is a function of x and t. So this is the gradient of chi. Uh, so that this p in the new vector potential p is equal to curl a prime. Now we know that a prime is equal to a plus gradient of chi. So this a is equal to a prime is equal to a plus this gradient of chi. So this can be written as gradient of a, uh, sorry, curl of a plus curl of gradient of chi. So which is equal to 0. That is curl of gradient of yes, scalar is equal to 0. That means P is equal to curl A prime, which is equal to curl A. So the transformation will not change the magnetic field. So it's a very important point. Now we choose a new scalar potential. Pi prime is equal to pi minus partial time derivative of chi. So, by definition, we know the electric field is equal to the minus partial time derivative of A prime minus the gradient of pi prime, which is equal to the A prime I have replaced as A plus gradient of chi, and the other one, the gradient of pi prime is equal to, from here, pi minus time derivative of partial time derivative of chi. So now you expand this first term. This will become minus partial time derivative of a minus the partial time derivative of gradient of chi, because here gradient is there. In the second term, if you expand this, you will get minus gradient of pi, minus of minus will become plus. So plus gradient of partial time derivative of chi. So we have to find which equal to, here you can see this is time derivative of gradient of chi. So gradient is uh, partial derivative, and here you have time derivative. Both are independent. So we can interchange the operators. But in quantum mechanics, it is not possible. But in classical mechanics, you can do it. So this second term and the fourth term will get cancelled. Both are equal. So finally, you will get minus partial time derivative of a minus a gradient pi. So this is what you get now. So exactly, this is exactly the original electric field. So by altering the pi, that is a scalar potential, nothing will happen to electric field. Similarly, by changing the vector potential, nothing will happen to the magnetic field. That is, when A is equal to A prime, which is equal to A plus gradient chi, then pi is equal to pi prime, which is equal to pi minus partial time derivative of chi. So this is called gauge transformation. This change in potential without changing the field is called gauge transformation. Now we will see about the Coulomb gauge. We know the Lorentz condition is divergence A plus 1 over c squared partial time derivative of pi is equal to 0. Consider a charged particle together with the pure radiation field. That is, there is no external charge distribution. This time derivative is related to external charge distribution. Since there is no external charge distribution, the second term will become 0. That means divergence of A is equal to 0, which is nothing but your Coulomb's gauge. We know that divergence of E from Maxwell first equation is equal to rho by epsilon naught. We know the electric field in terms of scalar and vector potential is minus the partial time derivative of A minus gradient of pi. So now you take divergence of this E. Divergence E, I have replaced E by this parameter inside the bracket, which is equal to rho over epsilon naught. So just now we have seen this expression. Uh, that is divergence of minus the partial time derivative of A minus gradient of pi is equal to rho by epsilon naught. Uh, s- so, this is equal to uh, divergence. See, first term, partial time derivative of divergence of A is equal to minus divergence of gradient is equal to del square pi is equal to epsilon naught. According to the gauge, Coulomb gauge, this divergence of A is equal to 0. So this minus, you multiply this equation by minus, then you will get del square pi is equal to minus rho over epsilon naught. This is nothing but the uh, the Poisson's equation. The solution to Poisson equation is 1 over 4 by epsilon naught integral rho x prime with x prime and t, which is a function of x and t, uh, over x minus x prime tq x prime. Uh, so, Coulomb gauge is used when there is no source. That is the important point. And this is the solution for Poisson equation. Here we came to the conclusion that Coulomb that is vector and scalar potential is invariance under Gauss transformation. That is one of the very important point. Thank you very much for watching my video and supporting me continuously.